Hey guys, there's only a few more things left that we have to learn before the AP exam. And today's lesson is about a rule called L'Hopital's rule. It's a French guy. Um, some people are saying that this is actually how he spelled his name, La Hospital, kind of apropos with today's issues going on. But whether you call him L'Hopital, like I grew up learning his name, or more recently within the last year or two, La Hospital, he found a way to make some limit problems easier. So I know you all love limits. You can't use it for every limit, but you can use it for any limits that result in indeterminate forms of 0 divided by 0 or infinity divided by infinity. This also applies to negative infinity divided by negative infinity or any combination of the two. So plus or minus infinity. Okay? Um, there are other types of indeterminate forms, but they are covered in later calculus courses. For the AP AB exam, you just have to worry about 0 over 0 or infinity over infinity. So here's the theorem. Basically, it says suppose that f and g are differentiable functions. We know that word, differentiable, on an open interval containing x equals a, so some number, except possibly at a. So if you remember back in pre-calculus, we had graphs that ended up with holes in them. So that's what this except possibly at a, x equals a means. You could have a graph that has a hole in it. That will be the only point of non-differentiability or non-continuity. So if you have the limit of f of x and the limit of g of x both go to 0, or if they both go to one of the infinities, then L'Hopital said that the limit of the derivative of the numerator divided by the derivative of the denominator as x approaches that number exists, or if it's plus or minus infinity, then the limit of f of x divided by g of x is equal to the limit of the derivative of f of x divided by the derivative of g of x. It's also true as you do left-handed limits, right-handed limits, or approach infinity or negative infinity. So this does not have to be a number. It could be a left-handed limit, a right-handed limit, or one of the infinities, as well as just regular old like numbers there. So some things to keep in mind in regards to the AP exam. It is not, I repeat, it is not the same as the quotient rule. Remember, the quotient rule says the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the denominator squared. When you are applying L'Hopital's rule, it is not the same thing as doing the quotient rule. This is a huge one. This, I would imagine that this is probably going to show up in one of the two free response questions on this year's AP exam. You must show that the individual limits, so the limit of the top and the limit of the bottom, go to 0 or to infinity. So in other words, I'll show you when we go to do an example. You will lose points on the AP exam if you don't do the individual limits. You may have to apply L'Hopital's rule more than once in a problem. And remember that exponential functions grow faster than polynomial functions. So for instance, this is x squared, and e to the x looks like that. Okay, so that actually will help you if you had the limit of x squared divided by e to the x as x approaches infinity. As you get further and further out on the x-axis, positive infinity, then the bottom is going to grow much faster than the top. So this eventually will go to 0. Okay, so let's do some examples. I'm going to switch pens here. I got these new erasable clickable pens. I'm so excited. Okay, so just as a review, way back at the end of pre-calculus, we did a problem similar to this. We have to find the limit of this rational function as x approaches negative 3. Well, as you can see, if you plug negative 3 into the top, you get 9 minus 9, which is 0, and negative 3 plus 3 is 0. So you get 0 over 0. So if you were to write this on the AP exam, you automatically lose points because this is not an answer. It's not a value. Okay? So please do not do that. What we have to do is we have to, if you remember, factor the top. It's a difference of two squares. Oh, and look at me. I get to use my eraser. Ha ha! That is amazing. X plus 3, x minus 3. And, oh, what is going on with my camera? Hang on, guys. Let me see if I can figure this out. Oh, okay. And the bottom stays x plus 3. Then we can see that the x plus 3 terms cancel. And this reduces to the limit as x approaches negative 3 of just what's left in the numerator, x minus 3. And then we can do direct substitution. Negative 3 minus 3 is negative 6. So here's the issue they have on the AP exam. Suppose you were to write that this limit is equal to 0 over 0, but we just found that the limit is equal to negative 6. You're making a statement that 0 over 0 is equal to negative 6, and that is not a true statement. So you want to avoid doing this, okay? So if we were, that's how we would do it the traditional way. If we're doing it with L'Hopital's rule, and I can guarantee you if they are giving you a limit problem on the AP exam in a free response question, it's most likely a L'Hopital's rule, okay? You kind of look at it by inspection. All right, well, we already know the top goes to 0, the bottom goes to 0. I know I can't write equals 0 over 0 because that's a big no-no. So what I have to do is I have to show the limit of the top as x approaches negative 3 is equal to 0. I have to show separately that the limit of the bottom as x approaches negative 3 is equal to 0. So once I show that they are both separately equal to 0, then I can apply L'Hopital's rule, and I'm going to write the original limit. Can you hear the TV in the background? It's funny. Equals, and now I can take the derivative of the top and the bottom. Don't forget your limit notation. We get the derivative of the top is 2x. The derivative of x plus 3 is 1. And then we can say, all right, well, 2 times negative 3 over 1 is equal to negative 6. Okay, so we have shown that the original limit is equal to the limit of the derivatives, and that's equal to negative 6. So I can link these all with equal signs because they are all equal. Okay, this is where we apply the L'Hopital's rule, showing that the limit of the original problem is equal to the limit of the derivatives. Writing this up here, this is called a linkage error. Not lim, linkage error. And we don't want any linkage errors. Okay? Okay, let's see if we can squeeze one more in before I have to go to a new video. I kind of like this purple. This purple worked nicely. Okay, so if you remember, well, it was a different purple. If you remember from pre-calc last year, we did problems like this, and it was if the degree of the top is bigger than the bottom, then there was no horizontal asymptote. If the degree of the bottom was more than the top, there was no the horizontal asymptote was y equals 0. And if the degrees were equal, then it was the ratio of the leading coefficients. Okay, and so in this problem, I know that the answer is going to be 3/2. But let's say that you froze on the AP exam and you didn't remember those rules. So we look at it and we say, all right, well, let's take the limit of the top, the limit of 3x plus 2 as x approaches infinity. All right, well, if x is getting really, really big, and then I multiply it by 3 and add 2, it's just going to continue to grow without bound. Let's do the same thing in the bottom. The limit of 2x plus 3 as x approaches infinity. Same thing. X is getting bigger without bound. We're doubling it and then adding 3. That's also going to infinity. So I'm showing that the top and the bottom of this limit both go to infinity. That allows me to apply L'Hopital's rule. Okay, so I'm going to write the original problem. 3x plus 2 over 2x plus 3, x approaches infinity, equals, now I'm going to take the derivative, x approaches infinity, the derivative of the top is 3, the derivative of the bottom is 2, and since that's just a constant, that is our limit. And that's what we knew from our shortcuts from pre-calc. Okay? All right, I'm going to stop this video and I'm going to make a new one for the next example.